All right, well, welcome to our second day of class, or still in our first week of classes. So hopefully everything has gone well for you for this first week. The plan for today, pretty straightforward. We already did the attendance for the folks who weren't here last time. And the plan for today is to just start with kind of a discussion of what is statistics and what are some applications of statistics, and then start the chapter one PowerPoint. The chapter one PowerPoint is uploaded to the Blackboard site for the course. And also I will pop it in chat in just a second here. Okay, it's also in chat just so that you can get to it more easily. So we'll work off of this PowerPoint for the next couple of class days. And then we'll also have a PowerPoint for chapter two coming up next. So that'll be posted in Blackboard as well. Are there any questions on anything? Um, I suppose we haven't gotten to any material yet, but any questions about the homework or syllabus or anything like that that you've come across?
I do have a question.
Sure.
I was looking to buy like the what's called the My Lab or
Mhm.
whatever. And there's two different options on CCAC's thing for your course, and I just wasn't sure which one I should get. Because I wanted to use like my financial aid personally instead of like paying out of pocket through like the website that you gave us.
Yeah, sure.
Um, can I just read off both of them and then you tell me which one it is, please?
Yeah, I'm actually just going to bring up the screen here. Um, yeah, so for anybody looking to get to the bookstore website, the easiest way is to go through our catalog here, find the section, and if you click that, there is a link to the bookstore site for that section. So that's the easiest way to get there. Otherwise, you have to go to this like CCAC bookstore, type in all kinds of information. Um, yeah, and basically we have these two options. And the main difference between the two options is this first one, it's oh, there we go. Wasn't letting me select part of it. But this first one up here includes, it's kind of hard to make sense of what they're saying here, but loose pages. It's a loose leaf version or loose bound version of the book. So it includes a physical copy of the textbook that like you would put in a three-ring binder. It's just a bunch of pages and you would either put it in a three-ring binder, or if you wanted to take it out chapter by chapter and put it in one of those like folders that has the little tabs that kind of fold. So this one includes the physical copy of the textbook as kind of a loose leaf textbook, as well as access to my stat lab. And this one down here is the standalone access card. So that only includes access to my stat lab. And you get the access to the ebook along with that. So if you want to use the ebook, this would be the way to go. If you want a physical copy, you could go this route, or you could buy the My Stat Lab access and then go on the secondary market and find a used hard copy. That might be another way to go about it. Um, as kind of a general rule, buying through the bookstore has some positives. You're a little bit insured if you like drop the class or something like that. And you can use financial aid. Some of that stuff works a little better, but the bookstore always does have a markup on anything they buy. Of course, they need to make kind of their cut too. So buying directly from Pearson can save you a few bucks. I want to say directly from Pearson is maybe like 110-ish. And from the bookstore, you can see the access code is like 130. So, you can save a little bit of money buying direct, but then that, does come with some downsides as well. Also, kind of as a side note, our textbook representatives are really good at working with us. So if for whatever reason, like the 18 weeks goes by and maybe the semester didn't work out for you or something, you withdrew from the class or dropped the class and come back next semester, you can usually ask your faculty member and they can reach out to the reps and they'll usually just give you another 18 weeks, another semester. So that's always something you can kind of um, kind of ask for, and our reps are pretty good at working with us with that kind of stuff. So did that answer your question?
Yeah, no, that was perfect.
Okay.
So much.
Yeah, yeah, sure. Um, Yeah, and these loose bound copies can be nice because again, you can just pull out a chapter or something, especially for like textbooks that are like three courses in one, like our calculus textbook is like 1,000 pages and it weighs a ton. Um, it has the plus of being able to pull out, say, just one chapter and keep it in a smaller, a smaller binder or folder or something. Um, but they also do tend to be a little harder to sell later on. If you wanted to sell that textbook on the secondary market, a loose leaf textbook might um, be a little harder to sell because people don't really know if all the pages are there, that kind of thing. Um, yeah. Any other questions? Okay. And then just a reminder that our first assignment on my stat lab is due this coming Sunday. Again, that the assignment labeled first assignment is really just to kind of make sure that you can get into the system, that you can open up homeworks, that the tech is working right. They should be pretty straightforward questions that you can just look up in the book or just go back to the index, look up a keyword, and then get the answer right. I think they're all multiple choice, so it's not meant to be a really, um, in-depth assignment or anything like that. It's just to kind of get you onto the system, get you poking around and figuring out how it works. Um, and if you don't have access to the textbook or access code yet, again, there's a 2-week free trial. So you can go on, you can sign up, get in there and use that 2-week free trial. And that gives you that buffer to figure out all the logistics on the back end, but still have access to all the course material. At this point, only about half of the class is enrolled. So I just wanted to make a note on that. Okay, if there aren't any other questions, then let's get into our discussion. So to kick things off, we'll maybe take about maybe 20 minutes, maybe 30 minutes to discuss the definition of statistics and then some applications or areas of interest where statistics might be used, some tools of statistics, that kind of thing, just to get an idea of the breadth and depth of this field. So anybody have any thoughts on what a definition of statistics might be? I mean, there's one in the textbook, but any of your own thoughts on how you would describe statistics?
Uh, Calculation of just average percentages and numbers.
Yeah, yeah. So it definitely involves calculation.
Analyzing different data points.
Yeah, we use a lot of data and statistics. That's an important side of things. So we can take some data and maybe it's not all that clear what this data says when I just have a whole bunch of raw data, but maybe if I compute an average or something like that, it's a little bit more interpretable. Any other thoughts? So my kind of working definition for statistics, I don't know, the book has some big long definition that's like a paragraph long, but I think that it's the process of converting nearly useless raw data into a more usable form. This is kind of my general definition of statistics. So we're taking raw data. Well, what is raw data? We'll think about that in a second, but that's just kind of the data as you initially get it from the real world. Whatever thing in the real world you're interested in, you gather some data regarding that, and that's what you're starting with. And we want to convert it into a more usable form. So a couple examples that I kind of like to use is maybe something like, okay, we're designing movie theater seats, and we have to decide how big to make them, right? The bigger that I make a seat, the less seats I can fit in the movie theater, the less people can attend a certain given showing. If it's a popular showing, that might be an issue, or the less profit I could make off of that showing. On the other hand, if I put in tiny seats, nobody's going to come to my theater. So I want to make my seats comfortable. So maybe I'm interested in something about the height, the typical heights of people in the population, right? I want to give them enough leg room. So my raw data might be something like I go out and I pick 1,000 random people and I measure their heights. So these, 1,000 heights that are like 6'1", 5'8", and so on. I have a list of 1,000 heights of randomly chosen people from the population of interest, from the people that live near this movie theater. That's my raw data. But if I just give you a list of 1,000 data points, that's probably not super helpful for you in designing how big these seats should be or what the typical person is going to look like. So I might want to convert this into a more usable form. I might want to say, what's the average height? Or maybe what's the max height, right? The max height, or maybe the min height, because if I design everything for a 6'8" tall person, then the 5'3" person is going to struggle to use that. I might choose to represent this with a, say, graphical representation. What's a graph of the heights? I might even ask for something a little bit more complicated, like something like what's the middle 90% of heights? Like, what's the 5th percentile and the 95th percentile? So maybe the seats will be uncomfortable for a few people who are either really short or really tall, but they'll be designed to be comfortable for the vast majority of people. Another example is maybe from finance, kind of one of my areas of interest. So if I think of looking at, say, the last 10 years of stock market data, maybe S&P 500 closing data, the price, so to speak, of the S&P 500 at the end of the day for each day, each trading day of the last 10 years. Well, if I look at that data, I just have a list of numbers, and it's going to be about 2,500 numbers long. If I just give you a couple pieces of paper with a list of 2,500 numbers, you can't really do anything with that. It's not really useful for you. But again, maybe I can look at, say, what's the average rate of return over that period? What's maybe the volatility? How much could I stand to gain or lose on, say, a given day? So what's the volatility? What's the kind of average return? What's the volatility in returns? Maybe what's the max or the min height? Or the max or the min value? I could look at a graphical representation. I might be interested in, say, a trend line. If I take this complicated wiggly path and kind of approximate it by a straight line, does that straight line kind of point up or down, or what's the slope? So there's a lot of things that I could do with this data that makes it more usable for me, that allows me to maybe understand it a little bit better, and then maybe with the ultimate goal of trying to make a prediction, right? What do I think that the market's going to do in the next month based on this past data? Or maybe not quite making a prediction, but making a design decision. If I want to make my seats comfortable for the middle 90% of people, what heights should I be designing for? Now, I think there's an important note here that kind of, as far as our understanding of something goes, we have raw data, and that's kind of the like bottom floor. That's the most basic bit of understanding that we have. I'm gonna try not to use the word information because I want to use the word information carefully in a minute here. And this is kind of my schema of how this works. This isn't, from the book or anything, but this is how I like to think about it. If I crunch this raw data a little bit, maybe I get an average or something like that. Maybe I construct a graphical representation. that gives me something that I can use to understand the system a little bit better, to understand in particular that data set a little bit better. And this is what I kind of call information, not in the technical sense, not in the sense of information theory or anything like that, but just in kind of the colloquial sense, this is what I would say is information. It's something that's useful to me to know about this. What's the average height of people in this area, something like that. From there, I want to take the data set that I have and that I maybe now understand a little better, and I would like to extrapolate. I'd like to go outside of that and make an estimate. I might want to say based on my sample of size 1,000, which isn't everybody in the population who might be interested in coming to this movie theater. But based on that data, can I make a guess about what this population looks like? What the average height of everybody who might come to this movie theater is, or what the distribution of heights of those folks is. Or I might go outside my data in another way. I might have my S&P data. I might say, okay, I understand the average rate of return over these past 10 years, the volatility of returns over the past 10 years. Can I make a guess based on that? Can I go outside of that and make a guess as to what I think is going to happen in the next month? And that's what I would kind of roughly term knowledge. So extrapolating from the limited data and information that we have, building up a model and making a guess that goes beyond what we have that's somehow greater than the data or the information that we directly have access to. And not just kind of a guess out of nowhere, but an educated guess that's supported by evidence, that's supported by this information and this data. And then I would argue that there is yet another level to this, and that's something like wisdom. That might be a question like, should I spend 40 hours this week analyzing the stock market so that I can make a little bit of extra money and not spend that time with my family, right? Should I design for the middle 90% of people? That excludes 10% of people who aren't going to be comfortable. Should I design for 95% of people? That's going to be more costly. That's going to, maybe result in lower profits, maybe result in other trade-offs, but there are going to be more people who are comfortable. How should I set this up? How many people should I attempt to include? If I try to design for literally 100% of people, that's going to be an absurdity, right? If I want everybody to be able to use my facility, it's going to be enormously costly to get that, that last person who doesn't fit the mold very well. So where are the trade-offs here? And that's where I think wisdom comes into play. And importantly, as much as I would like to believe that math and stats can answer all questions, stats really deals with these first three. And then this idea of wisdom, this is maybe something more related to philosophy or religion, depending on your perspective on it. So I always say that we leave wisdom to the philosophers and the pastors. So, and I think it's important that we understand that there are questions that stats can answer and math can answer, or any field of study. There are questions that it can answer that's in its ballpark. And there are questions outside of that, and we ought not tread in territory that we're not designed to tread in. So if you say, I want to design for the middle 90% of people, if that's the decision that you made on some moral or ethical or whatever grounds, then we can use stats to answer that question. We can't use stats to say, is 90% a good number, right? That's a question that's outside of stats. Similarly, like when we're doing hypothesis testing and we're talking about the significance level, essentially the maximum error rate that we're willing to accept, how often are we willing to be wrong about a scientific conclusion? Stats can't really answer that for you. That's a question that's more of a philosophical question, right? How often can you be wrong? You can't say, I don't want to ever be wrong, because then you can really never say anything. So what error rate are you willing to accept? so that your conclusions are in general valid, are typically valid, that people have a high degree of belief and confidence in what you say, but that you can actually say something, right? If your standard is so high, then you can never say anything. So where does that trade-off lie? Again, that's a question of maybe something like epistemology, like how do we say that we know something and that something is true? That's not a question we can answer, but if you say, I'm willing to accept a 5% error rate, if you come up with that number, then stats can go from there. So I think it is important just to note that distinction that there are questions even directly related to stats that are outside the realm of stats that we just have to set a number and then stats can do the calculations. So we can answer some things, but not all questions. Okay, so that's kind of my spiel on what is statistics. And the goal of this course is going to be to look at a little bit about how do we gather raw data? How do we get this raw data in the first place? This is not a course on experimental design, so we won't go too far into that. But we're mainly going to focus on this step here. If I have some data, how do I crunch those numbers and get different representations of the data to understand the data set a little bit better? And then how do I do this step here? If I know the average, the volatility, these kind of things, how do I take that next step and make some inferences, step outside of the data set to try to understand something about the greater world as it pertains to whatever we're studying. Okay, so let's think a little bit about some applications of statistics, well, some applications of statistics, and some tools or techniques used in the field. We've already listed a couple, so I'll just kind of write those down here. We mentioned averages, percentages, or proportions. So that might fall under tools or techniques. The average or proportion. And what are some applications? What are some fields where statistics is used? Any thoughts on that?
Maybe baseball to see how far the ball could travel potentially.
Yeah, so baseball, I mean, these days it's super fun to watch baseball because you get to complain about the umpire, right? Like they throw the ball and they have the strike zone right there and where the ball ended up and how fast it was going and whether it was a curveball or a slider or whatever. And then, of course, it's a little bit outside the box and the umpire calls a strike and you can say, it's a terrible call, like, or like how far it goes, they know right away, like it traveled at this arc and or at this launch angle and went this distance, or golf also has that kind of stuff. So yeah, there's tons of stats in baseball or sports in general. Yeah, so all of these kind of things like, the distance the ball traveled on a hit or the speed it was going on a pitch or the number of pitches that that a pitcher threw or any of that kind of stuff. As kind of a side note, there's this this thing in baseball called saber metrics. If you've seen the movie Moneyball or if you've read the book by Michael Lewis, he actually writes about mostly finance stuff, but he wrote that book. I'm not exactly sure why. I have it. I haven't read it yet. They talk about some of this stuff, and basically what sabermetrics is it's statistically analyzing each player to say, essentially, in some sense, what's the value of that player to a team. So if a player hits a bunch of home runs every season, they can say, okay, if you had this player instead of some other player on the roster, they would hit all these home runs and you'd on average win this many more games. And that might translate into, getting into the playoffs or something when you otherwise wouldn't. So this idea of sabermetrics has been around for probably, 30 years or more at this point. Yeah, ton of stats used in sports. Any other areas?
I have two, but I'll choose one given it's an election year politics.
Yeah, definitely. I couldn't hear you super clearly, but I think I heard you say that it's an election year in politics. Yeah, definitely. So proportions, what percent for candidate A versus candidate B. Neither of them end in A or B, right? Okay. uh, I always try to keep it neutral, right? Like, yeah, politics and religion, the two fields you don't want to talk about with most people. So, yeah. So, where do we use stats? Well, maybe in exit polls, right? So people come out of the polls, and we're trying to get an idea earlier in the day what the poll is going to look like at the end of the day, because everybody in the world is very impatient, and we don't want to wait the 12 hours or something. Um, so they're saying, at noon or something, that we think this candidate's leading by this amount based on random sampling of the people leaving the exit polls. Or maybe even way ahead of time, they're maybe calling people randomly on the phone and saying, who are you going to vote for? And trying to make an estimate on that basis. So that might take raw data and move it into information. And on that information, if one of the candidates, whatever they're called, support staff or whatever they are, if one of the candidates, like election folks, are doing these polls and they say, oh, well, in this area, you're winning by a huge margin, maybe they're not going to spend so much money advertising in that area or book a bunch of campaign stops in that area. And maybe on the other hand, if in this other area you're losing by a huge margin, well, we're not going to waste our time there. That's a lost cause. But here's a swing state, right, is what they sometimes call them, or here's an area that kind of could go either way. Maybe this is an area where you're going to want to spend most of your resources and most of your time to try to, tip the balance in your favor, where you're not wasting your time by engaging in a lost cause, and you're also not wasting your time by, getting an 80% win instead of a 70% win. Effectively, a win's a win in most places. Yeah, so definitely politics is a huge one. Any other areas?
Finance?
Yeah, definitely finance. Yeah, so finance generates tons and tons and tons of data. This is just an example from, say, the S&P 500, but every individual stock, every individual bond, every one of these indices, maybe the Dow Jones, they all have all of this data that they're constantly generating. And we can do all of this number crunching on all of that data. Yeah, and why do we care about that? Well, should I invest in a risky stock or a safer bond? Should I, invest in a mutual fund instead, a collection of stocks? What are the costs and benefits of that? If I invest in something riskier, typically I'm going to get a higher rate of return, but at a higher risk. If I'm about to retire, I probably don't want that. I don't want to see my portfolio get cut in half right before I retire. That's going to really throw a monkey wrench into my retirement plans, my confidence and happiness, and so on. I might want to go with something a little safer, closer to retirement. On the other hand, if I'm in my 20s and my portfolio gets cut in half, it's got plenty of time to recover. I'm not super worried about it. Personally, I think that people blow a little bit out of proportion the severity of a crash right before you retire. If you set up your portfolio reasonably at all, it doesn't really matter. Because at least historically, the market's always recovered in a year and a half or so. So as long as you have some assets in a pretty safe place, you're good. But that's another discussion. But yeah, definitely finance, another field where we use tons and tons of stats. Any other thoughts? Well, current
My other
events, sports with the Olympics. That was another one that was kind of recent. I think somebody, yeah.
I'll give my other one.
Yeah.
Medical research.
Mm-hmm. Yeah, absolutely. Medicine uses a ton of stats as well. So in medical research, there's a couple reasons they use a lot of stats. One of them is, say, if you're in a clinical trial, so I have some new drug that I want to bring to market. I think it's going to cure some certain disease, but I don't really know how risky it is to people yet, right? I don't want to just like run a clinical trial of 2,000 people if I think that's how many people I need to establish the evidence I need to establish, because that puts all those 2,000 people at risk. So maybe what I would do is I would take a small number of people and I would start the clinical trial with them. And I would basically see, with this 50 or 100 people, a month later, 2 months later, does it seem like they're having any really bad side effects? If not, I'm a little bit more confident that the drug is safer. So then maybe I expand the trial to, 300 people, follow them for a couple months. If they're still not an unreasonable number of serious side effects, maybe then I expand it to 1,000 or 2,000 people. So I can use the information that I gain along the way to adapt the study and, hopefully minimize risk to the participants. So that's one example. Another example is we have electronic medical records now. So we have tons and tons and tons of data that's all stored electronically and can be mined. So if I want to know, is there a correlation between, or is there a correspondence between this disease and this behavior, then I can look back and I can go through the electronic medical record and just say, you know, how many people have this disease and do this behavior versus how many have this disease and don't do that behavior. Does it seem like the folks who do that behavior are at a higher risk for this disease? Things like that. Yeah, I mean, medicine uses a ton of statistics. I would argue probably, I don't know. I mean, I'm a little bit biased because my background's in finance and my wife's background's in medicine, but in my mind, like finance and medicine are the two areas where, probably the most stats is used. I mean, all these other areas are certainly areas where stats is used a lot. Any other thoughts on some areas where statistics is used a lot?
The housing market potentially.
Yeah. So economics, the housing market. Yeah. So I have a friend who works at the Fed and he studies housing markets, rent prices, house prices, those kind of things. What are the contributing factors um, to the recent increase in housing and rent prices and so on. Yeah, and they also use a ton of data, a ton of statistics to analyze that. So a lot of times when we use stats, we're working off of limited information and we're trying to extrapolate and figure out the bigger picture. But in something like that, in say the housing market, you pretty much have complete information. You can pretty easily get records. I mean, not easily for you and me, but easily for people that have, big research teams. They can get information. They can have all the information about, you know, most all of the house sales, say in a certain area. And then the question becomes, okay, well, if we have all of that information, if we're not, say, taking a small sample and trying to extrapolate and say, how is this representative of the population? If I have access to the whole population of data, basically, which I might have in something like this, or even in finance, right? I can just look up all of the stock prices. My my interesting question might be something like, okay, but what's contributing to that? What are the causative factors that are leading to this change in the housing market or this change in the stock price? So I could go still outside of the data that I have and I could ask, well, something is giving rise to this, right? These are people either trading houses or trading stocks, and they're making decisions on some basis. What are the bases they're using to make their decisions? Any other thoughts?
Social services.
Yeah. 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 I mean, money is scarce, right? And we have to decide when we allocate money to let's just say roughly the region of helping other folks. How should that money be allocated, right? Where should we allocate it so that it will help the most folks in the greatest need or something like that? How do we make those decisions? And I'm not all that familiar with that decision-making process, and I imagine there's probably a lot of politics and things in it too, but maybe ideally we would want to imagine a situation where we would have this chunk of money and we would go out and we would kind of sample the population and get an idea of what folks have certain needs and what needs are the greatest. Should we put more of the money toward helping folks with food, or helping folks with schooling, or helping folks with housing, or just a universal basic income kind of system where just giving them the money and letting them kind of allocate it as they see fit. Medical resources, do people need a lot of medical care that they're not getting? There are probably all going to be all of those needs and not enough money to go around. So how do we allocate that money? Again, some of the answer to that question, or a lot of that, falls outside of statistics, but maybe the statistics can be used to help inform that decision-making process. Any other areas?
Healthcare?
Did you say healthcare?
Yes.
Yeah, healthcare. Yeah, so it kind of falls under medicine, but we were kind of talking more in the realm of research up here. Yeah, so healthcare, I mean, we saw during COVID how important it was to really track that number of people needing hospital care versus how many beds were available. And, when those two numbers were getting close to one another, that was when maybe, more extreme measures were taken to try to keep those from being upside down, from having more people needing hospital beds than beds available. Again, there's a question of, should we have done this thing or that thing? But at least we can say that I think the statistics and the understanding of those numbers and the projections at least informed that decision-making process. Yeah, maybe in an area like education, right? Just kind of speaking of COVID, we see that a lot of students kind of had a couple of years during school where things didn't really go so well, right? Things didn't really go to plan. And what was the impact of that on student learning, or on test scores, or on preparedness? And how does that fit into the conversation of how to remediate that and kind of come out on the other side? And yeah. So I mean, we use a lot of stats in education, looking at things like pass rate and student success, and on the financial side, which the folks on the academic side are fairly insulated from this. So I'm happy that there are people like, our college president and our campus presidents and those kind of folks doing the financial side, so we don't have to worry about it. But they worry about things like enrollment and how that impacts the budget and all of that. So what's our projected enrollment for a given semester, and then what budget do they set based on that, and so on. All right, so that gives us, I think, a pretty good assortment. Is there any burning application anybody wants to state, or should we move on? Okay, so any ideas of some tools or techniques? This is a little bit more technical, so if you don't have any thoughts here, that's not a big deal, but we already talked about some things, like I might be able to take some raw data and get an average, or get a proportion, the proportion of people who are going to vote for this candidate versus that one. Any other ideas of something I might do with raw data to help me understand the world a little bit better, or to help me understand that data a little bit better? Well, one thing I might do is I might draw a graph, right? I might take this stock market data and turn it into a graph I can understand, say, 2,500 data points in a graph like this a lot more easily than I can understand them just written down as numbers.
So like a specific equation we could use for it?
For a graph, or
No, like to get like data, I guess, specifically. Like for statistics. To like add on to what you're saying.
yeah, we definitely do have formulas for like how to compute an average, or different formulas for, say, volatility, right? A stock that looks like that versus one that looks like this, kind of on average over this time period, they did about the same, but one of them bounced around a lot more than the other. So we have definitely formulas to use to calculate these different, say, types of averages or different measures of volatility. Doing a lot of this by hand requires a lot of work, but we can use things like, say, Excel, Microsoft Excel, or other more sophisticated tools like the programming language R, or Stata, I forget how they say it, or S plus, S plus, or SPSS. I'm not sure if it's called Stata, but S plus and SPSS are definitely out there. So there's a bunch of software packages that will do a lot of this number crunching for us. These days, even things like Python and more general programming language, it can do all kinds of things. You can, write a web browser in it, you can write an application in it, but you can also have it use some of its libraries to work with data. So there's a something called Pandas that's a data analysis package. There are several things like that in Python. So we can use technology to help us with this. These days, even AI. So AI uses stats to kind of build its models. But also we can say, hey, some artificial intelligence, network, like, here's a bunch of data, summarize it for me, or something like that. And it'll likely come out with something pretty reasonable, and might come out with something completely unreasonable. So I'm not a big fan of AI yet. I think that the amount of time and effort that goes into checking the results is probably, for most people in most cases, more than the amount of time and effort it would take you to just generate the result yourself. Keeping in mind that our brains are inherently lazy. So if we're creating something, we're kind of constantly checking it as we go along. But if AI gives us something, if it gives us 5 pages of something, we're probably going to like start checking it really carefully, and then half a page in, we'll get a little lazy and kind of skim over the rest of it, even if we don't realize we're doing that. So I'm always a little hesitant to trust something that somebody else has done. And so I don't know, maybe it'll take me a couple years to get on board with AI. But statistics is both used to create AIs and can be done by AIs. And then we have some other inferential techniques. So things like saying, for this stock, it bounced around a bunch, but what was kind of the overall trend line? We would call this a regression line. We'll talk about that near the end of the course. In medical research, we use a lot of hypothesis testing. So I have hypothesis A versus hypothesis B. I collect some data, and I want to decide which one to go with moving forward. Which one seems to be the one that I'm going to choose to work under from this point forward. So that's kind of what hypothesis testing does. Again, we'll cover that near the end of the course. Related to this is the idea of confidence intervals. So maybe my best guess at the average for a population based on the sample average is some number, but how good is that number? What's the kind of range of reasonable possibilities that population average can be based on the data that I got? All right, are there any other thoughts on applications of stats or tools or techniques? So hopefully everybody was able to see something in here that really resonates with you, where you say, okay, I can definitely see how this field could be applicable to my future career, my field of study, my hobbies and interests. Okay, so now the plan is to start into the chapter 1 PowerPoint. We have what I suppose about an hour or so left. So we'll see how far we get today, and then we'll pick up where we left off next time. So give me just a minute to shift my windows around, and then we'll be right back. Oh, I see there are some chat messages that I didn't see. Oh, okay. Yeah, if you guys want to set up a group chat, feel free to. Okay. But let me swap my my windows around here, and we will get right into it. All right, so we have the chapter 1 PowerPoint. Again, I posted this in chat earlier. It's also on the Blackboard site, so you can get it there as well. And the oops, I did forget the quote of the day for today. So the quote of the day for class today is from the Greek philosopher Epictetus, from his book, usually just called Discourses. This is a pretty loose translation. But the statement conceit of knowledge gets in the way of learning. So if we think we know everything, we're not going to be seeking out new information. We're not going to learn. We're not going to progress in our knowledge or understanding of the world if we already think we know everything. And kind of related to this are questions like, what information should be trusted, right? Not just should I trust the information that or the outlook that I have, but what information should I bring in? That's not an easy question to answer. People like to say, oh, well, trust information from experts, but if you ask them how they define expert, it usually boils down to somebody who's saying the things that I agree with. That's how I define expert. And somebody who says things I disagree with, I call them a fraudster or something like that. So it's also not easy to define expert. So yeah, you might want to say something like, oh, somebody who has a degree in the field, but you can find lots of examples of people with degrees in a certain field that a person would disagree with and not want to call them an expert. So anyway, just something to think about again with our kind of discussion of data versus knowledge and all of that. We don't want to be too conceited in our knowledge. We want to be open to new information coming in. And we have a second bonus quote for today. This will probably be the quote of the day for someday in the future. But this is from statistician George Box, the famous, the Box-Cox model, the Box-Jenkins model. So famous statistician. And he said this quote, which I think is kind of our guiding quote for this whole course and maybe for the whole field and maybe for really all of the applied sciences, is essentially all models are wrong, but some are useful. Right? We're developing models to hopefully help us understand the world a little bit better. We understand these models aren't perfect. They're not perfect representations of the world, and we can't extrapolate perfectly to understand the world from them. But hopefully they're useful. Hopefully we're constructing models where we're better off after the construction of the model and the use of the model than we were before. And that's really our goal here. All right, so this is kind of the longer definition of statistics, but as I kind of mentioned, my working definition is that statistics is the process of converting nearly useless raw data into a more usable form, into usable information, and then maybe we would call it knowledge. Okay, so a couple of important ideas here. The idea of a variable. At first glance, this is just kind of the same kind of idea as, say, any other math class. You have variables. A variable is something that can take on different values. Data are the values that the variable can assume, and a data set is when we go out into the world and we collect different data points, we see actual instances of this variable in the real world. We see individual people's heights, we measure them, we collect them together. That's a data set. Random variables are variables whose values are determined by chance or by randomness. Um, kind of a little, kind of a little short digression here. We'll talk a little more about this in chapter 4. When we say randomness, it's not exactly clear what we're talking about. When I say that a variable is random or that it's determined by chance, it's not 100% clear what I mean by that. So there is this idea in our world that things are fundamentally random. And this really comes from quantum mechanics and a lot of the crazy stuff that happens with quantum mechanics, that, if you look at an electron, like you don't, like its spin is actually random until you measure it. It like essentially doesn't have a spin in some sense until it's measured. And then like whether it's spin up or spin down is completely random, at least as far as we can tell and as far as the best theories suggest. We're not going to think of randomness like that. That's just a little too far to go outside of kind of our normal everyday experience, right? If we get down to that order of magnitude in some crazy physics class, then you have to really reimagine what you mean by this. When we say random, really what we're thinking of is something that's chaotic. And that might not be super helpful to you, but chaotic means something very specific in mathematical terms. The best way I've heard chaos described is it's where the present state, where understanding the present state allows you to perfectly predict the future state, but the approximate present state does not predict the approximate future state. So if I have exact knowledge of the present state, then I can, in theory, with exact calculation, get exact knowledge of the future. But if I deviate even a little bit from my present understanding, then my ability to predict the future basically goes out the window. So an example of this would be something like a die roll. If we roll a 6-sided die, I mean, it's basically just going to follow Newton's laws. In theory, if I, had some kind of robot or camera system or computer system that could look at that die leaving somebody's hand and could predict exactly, what's the speed that it leaves their hand, the direction, what's the rotational velocity, and all of that kind of stuff. And what are the interactions with all of the things it's going to bounce off of going to be like? Then we could say where that die is going to land. Is it going to land on a 1 or a 6? And this seems like, in theory, something that we could do and probably could do if we had an accurate enough system. But if I actually pick up a die and throw it, there's no way that I can do that, right? And even somebody who's really, really smart and really good at this and has practiced for a very long time is still not going to be able to say, when I pick up a die and throw it, by the time that it lands, they're not going to be able to say what number it's going to come up. And that's because if I change even a little bit, kind of the speed that I throw it at, or the rotational speed that it's let go at, or what it bounces off of, or how it bounces off of them, change any of those even a little bit, and it could change from a 1 to a 6. It's not going to be like if I change the speed a little bit, it'll go from a 1 to a 1.1. It could change from a 1 to a 5, right? So that's what we think of when we're thinking of random. We're thinking of random being a mathematical abstraction of this idea of chaos, of this idea that me personally or people in general really can't predict an outcome. We just, don't have the chops for it. We don't have the data or don't have the computing power or don't have the time and money to and resources to do it. So we overlay this mathematical idea of randomness onto the system, and we use that as a model to work under. So I think that's an important point, is we're not saying that like a die roll cannot in theory be predicted, or that a coin flip cannot in theory be predicted. In theory it could, but in practice it can't. So we're not able to do it. And that's an important distinction, because what I can do in practice changes depending on who I am, what resources I have, how much time and effort I want to put into understanding this. So, okay. So moving on to the next topic, and again, we've already introduced some of these ideas through our previous discussion. We have two main areas of stats, that's descriptive stats and inferential stats. And kind of roughly speaking, descriptive stats is this first step here, taking raw data and trying to crunch it and get more information that helps us understand the data set better. And inferential stats is kind of, roughly speaking, the second step here, where we try to go outside of the data set and say something bigger about the real world. So descriptive stats, again, working kind of inside of the data set, I might find ways to organize the data, to summarize it, to present it maybe with a chart. I find ways to understand the data set itself better. That might look like computing an average, or finding the volatility, or presenting a graphical representation of that data set. Inferential stats generalizes from samples to populations, going from the data that I have to the entire population that I would like to study. So things like hypothesis tests are an example of this. Things like making predictions. What do I think the stock market's going to do next week based on what it's done the last couple months? This uses the mathematical structure of probability. That's what inferential statistics is kind of built on. It kind of marries the two ideas of descriptive stats, and this mathematical structure of probability brings them together. And, like I mentioned, maybe the most widely used maybe inferential stat that people often know about or often care about is hypothesis testing. And that's due to its prevalence in the medical literature. So we brought up this idea of population versus sample. What's the difference between these two, a population versus a sample? Well, a population, what I like to think about is, if I want to make a statement, I might want to make a statement like the average income of Pittsburghers is blank. That's the statement I would like to make. And from that statement, I can infer my population, all Pittsburghers, all people in Pittsburgh. Now, if I was going to be really careful and design a study, and I would have to be a little more careful about what I mean, does that include people who work in Pittsburgh but don't live in Pittsburgh, or who live in Pittsburgh and don't work in Pittsburgh? Does it include, kindergarten kids who make zero income, or, right? So I'd have to be a little more careful about how I design that, but we're going to stay away from those nuances and just say, okay, if I want to make a statement, the average income of Pittsburghers is blank, that's my population, all Pittsburghers. Now, I probably don't have the resources, the time, the energy, or even the cooperation to go out and visit every single Pittsburgher, get their income, and then bring all that data together, crunch it, report it, or report an average for all that data. That's what I would, in theory, would like to do, but I almost never can do that. I'm limited by resources and so on. And even if I could do that, why would I spend that much resources over here when maybe I have 10 other questions that I would like to answer as well? And I could divide those resources and answer all of these questions to the same level of effectiveness. Why would I devote all of my resources to one? So what I almost exclusively will do is, instead of studying the entire population, the one that I want to make a statement about, I'll instead take a sample. I'll say, okay, here's these, let's say 600,000 Pittsburghers that is my population. I'll sample 1,000 of them. On average, 1 out of every 600 people will get chosen. If I do this properly, if I do it randomly and so on, then I get a data set. I have sample data, and I would hope that if this data is representative of the population, it's kind of a microcosm. It's kind of just the whole population shrunk down in scale from a size of, say, 600,000 to a size of 1,000. So with the sample, I can do similar things. I can compute, say, a sample average. And if I do my sampling well, I would think that that sample average is going to be pretty close to the population average. So I could report a sample average income. This is the average income of a sample of size 1,000 taken from the population of Pittsburghers. And I would say that, well, the information communicated there, or the knowledge communicated there, is seemingly effectively the same as saying this is the average income of all Pittsburghers. And that's where things like confidence intervals and hypothesis tests and so on come into play. So again, just kind of to summarize, the population is what I would like to study, but I almost never have access to it, either because of resources or cooperation or whatever. The sample is hopefully a microcosm of the population, just kind of the whole population shrunk down in scale that I typically do have access to. And that's what I'll be studying. So I want to get an answer about the population, but practically speaking, I'm stuck with getting an answer about the sample. And a decent bit of statistics is saying, how does that answer about the sample relate to the answer that I want about the population? So related to these ideas, we have parameters and statistics. And a parameter relates to a population, a statistic relates to a sample. Kind of easy to remember with the P goes with P and S with S. So I might say that the population average, the true average income of all people in Pittsburgh, I would refer to that as a parameter. But the sample average, if I take a sample of size 1,000 and get an average of that smaller data set, I would call that a sample statistic. So here's just an example. Of the 1,300 or so people sampled, 12% of them were found to be diabetic. That's a descriptive statistic because it discusses only the data set. A seemingly similar statement, based on a study involving 1,347 people, we estimate that 12% of all Americans are diabetic. Well, we certainly did not sample all Americans, or so we certainly did not look at every American and decide whether they were diabetic and come up with 12%. We're basing this on a sample. But we're saying that if this is a large enough sample, if it's sufficiently representative, I think the results of that sample can be extrapolated to all Americans. And that's making an inference. I'm taking this 1,300 or so data points and trying to extrapolate it to the 350 million or so Americans. Is that a good thing to do or not? Again, that's a question that we'll try to answer in a little more depth later on in the course. Okay, so moving on to variables and types of data. Some of this stuff coming up here is going to seem a bit esoteric. You're going to say, why are we looking at all these definitions and so on? But there is good reason for this. And the reason we'll start seeing it even as early as chapter 2, when we have to decide, we have several graphical techniques to represent some data. Which technique should I use? Should I use this one or that one or a different one? And that's often related to what type of data I'm dealing with. Or maybe in chapter 3, when I'm deciding, okay, there's a lot of different things that kind of are an average. which one of those should I report? Should I report the mean or the median or the mode or the mid-range? Well, maybe I would consider something about the type of data before I would make that decision. Okay, so let's move into this. So the first way that we can split variables is between qualitative versus quantitative. Qualitative variables are variables that can be placed into distinct categories, where quantitative, these tend to be numerical and they have a natural ordering or ranking. So, uh, so let's think of some variables. And let's categorize them as qualitative versus quantitative. So what are some things that I might be interested in measuring? We had a lot of applications, and so previously, what's something I might be interested in measuring or knowing more about? Well, one thing I guess might be, say, people's heights, right? So if I think of somebody's height in inches, is that qualitative or quantitative? Well, it does have a natural ordering or ranking. Somebody who's 6 feet tall is naturally taller than somebody 5'10", who's taller than somebody 5'3". So something like height would go under quantitative. Where, say, for politics, maybe political party, you're a Republican, you're a Democrat, you're a Libertarian, you're an independent. The party that the candidate is registered under, that would be more qualitative. There's not a natural ordering or ranking. Yeah, you could order them, you could maybe put them in alphabetical order, but that doesn't intrinsically have something to do with the nature of that political party. It's just, some arbitrary way to order them, if you have to choose an order. But these are distinct categories, right? A person who's running as a Republican can't also run as a Democrat. Any other examples that anybody can think of?
Race could be qualitative.
Yeah, so race or ethnicity. Yep. Any other thoughts? So we could have some medical characteristics, things like, say, weight. We could have, for instance, disease status like diabetic.
Age would be quantitative.
Yeah, exactly. Age would be quantitative. Yep. Anything else?
Income might be
Experiment.
qualitative.
Sorry, I think that was, I didn't catch either one of those.
I said experiment.
Yeah,
It's
so
quantitative.
so experiment, yeah, we could do an experiment to kind of decide, say, what proportion of people are diabetic or non-diabetic, or to figure out maybe the average height or weight of a certain group of people.
I had said income may be qualitative.
Yeah, income. I would tend to put income under quantitative. So for qualitative, I mean, I suppose if you were doing something, so like maybe source of income, like job, something like that would be qualitative. So like, are you, do you work in education or in finance or in, what can I think of any in medicine or, but I think, amount of income like salary or something like that would be quantitative. Somebody who, makes a higher dollar amount per year has a higher salary. It's fundamentally kind of ordered, but job type that what you choose to do for work is doesn't really have a natural ordering or ranking. So things like maybe blood pressure or heart rate, something like that. We could have something like number of students in, say, a classroom or enrolled in a class, something like that. We could have something like, say, a die roll. The result like 1, 2, 3, 4, 5, 6 coming from rolling a 6-sided die. So something, what about something like, say, a zip code? Would zip code be qualitative or quantitative? Any thoughts on that?
Quantitative.
Yeah, it seems like it would be quantitative because it's a number, right? But if I said city, like, Pittsburgh or Cleveland or Wheeling, would city be qualitative or quantitative?
Qualitative.
Yeah, I think city would be qualitative. There's not really a natural ordering or ranking to different cities. They're different geographic locations. So I would probably also put zip code, at least in most cases, under qualitative, actually. Even though it's a number, it really just is kind of a numerical representation, basically, of a city. Now, there is a little bit of something to be said that numbers that tend to be closer together also tend to be more geographically closer together. So you might draw something from that. But I think most of the time we would think of, say, things like zip code or things like, let's say, a social security number. Even though those are numbers, they're really just kind of identifying like a certain person or a certain geographic location. So I think we typically put those under qualitative. Something like, say, a grade, A, B, C, D, F. Even though those are letters, I probably would actually put that under quantitative. Mainly because these have a natural order to ranking, right? I mean, I think everybody in here would much rather have an A than a C. So an A is a better grade than a B is better than a C. They're a little bit less like qualitative, where there's not a natural ordering or ranking, there's just kind of categories to place into. These are distinct categories, A, B, C, D, F, but they come with this natural structure of a natural ordering. And that's really what we're trying to do here, is we're trying to split out, in some sense, what does the underlying structure look like? Is it just kind of a bunch of different bins that are on equal footing with one another? Or is it a bunch of bins that have some kind of hierarchy? Okay, so next we're going to talk about discrete versus continuous. Give me 1 second here. Okay, so next we're going to talk about discrete versus continuous variables. So discrete versus continuous is a further classification of quantitative. So we're going to look at the quantitative variables and for each one discuss whether we think it's discrete or continuous. So The distinction is a little bit hard to make clear here, but here's an attempt. Discrete variables assume only values that can be counted, where continuous variables can assume an infinite number of values between any two specific values. And I think another way of thinking about this is for a discrete variable, if you look at one possible value for that variable, you can always say what the next possible value is. Where for a continuous variable, if you look at one possible value, there's never a next possible value. If you try to hypothesize and maybe a next possible value, you can always come up with some other allowable value in between those two, in between the one you started with and what you thought might be the next one. Or another way to think about continuous variables is these are measurements that have to be rounded due to the limitations of our measurement system, whether it's a device or whatever. And if we had a more accurate measuring system, we could get more decimal places of accuracy. Note importantly that continuous variable has nothing to do with kind of time. It has nothing to do with like whether we're continuing to collect data or not, or something like that. A lot of times students kind of try to impose some element like that, but it has nothing to do with that kind of a thing. It's a question of how we're measuring this data. Okay, so if we think of, let's start with something like, say, number of students. Would this be discrete or continuous? If I have 2 students in a class, what's the next allowable number of students in a class? Well, that would be 3. If I have 3, the next allowable is 4, right? Or it assumes only counting values, 1, 2, 3, 4, and so on. I think this would be discrete. Or another way of looking at it is if I have one classroom with 2 students in it, another with 3 students in it, is it possible to have a third classroom that has a number of students that's strictly between 2 and 3? Well, no, it's not. So it can't be continuous, because if it were continuous, there would be more values between any 2 specific values, like 2 and 3. There would be an allowable value between the 2. But since that's not the case, it's not continuous, must be discrete. On the other hand, if we look at something like height, maybe height in inches, well, I could have one person who is 70 inches tall, let's just suppose exactly 70 inches tall, another one who's exactly 71 inches tall. Could somebody be a height that's between them? Sure, you could be 70.5 inches or 70.1 inches or 70.001 inches. Or another way of looking at it, if I measured somebody's height very crudely, I might say, okay, you're about 6 feet tall. If I got a more accurate measuring device, I could say, oh, maybe you're like 5'11.5". More accurate still, maybe I could say you're 5 foot and 11.6785 inches tall. The more accurate the measuring device that I get, and perhaps at some point, the more accurate or the more carefully that I describe what I mean by height, the more decimal places of accuracy I can get. This would be continuous. So what about something like, say, a die roll? Discrete or continuous? Any thoughts?
Continuous.
So if it was continuous, then between any 2 outcomes, I should have another outcome. So like I could roll a 1 or I could roll a 2, but is there anything between 1 and 2 that I could potentially roll?
No, I guess you're right. Yeah.
Yeah, I think this one's going to be discrete because, again, I could come up with numbers like, say, 1 and 6 where there are instances between the 2, but I can also come up with numbers like 1 and 2 or between 5 and 6 where between those 2 numbers, there are no other allowable values for that variable. Or another way of looking at it is if I have the number 2, I can say the next bigger number that I can get is 3. From 3, the next bigger number I can get is 4. I can't say something like that with, say, height, if somebody's, 70 inches tall, what's the next allowable height? Well, if I wanted to say 71 inches, they could be 70.5 inches. Or if I wanted to say 70.1 inches, somebody could be 70.01 inches. That would be a number between those two. But something like weight, well, would weight be discrete or continuous? Either weight of a person or weight of whatever we want to weigh doesn't really matter.
Would it be continuous?
Yeah. Yeah, weight would be continuous. Yep. Again, we can look at it either way. We can say, okay, if something weighs, 1 pound, so let's say 16 ounces, is there a next allowable weight? And if we're tempted to say, well, 17 ounces, well, something could be 16.5 ounces or 16.1 ounces. Or in between any two given weights, we can find more allowable weights, more possible weights that something could weigh. Something like, say, blood pressure, that's probably also continuous. Now, we typically report blood pressure using whole numbers because that's kind of convenient and that's the scale that is helpful for us. We don't really care if somebody's, what systolic, is it systolic that's the higher one? I think so. Because asystole means you're not contracting, right? So we don't really care if somebody's systolic pressure is 120 versus 120.1. That's not a big enough difference for us to make a difference in treatment or in recommendations or whatever. We care about like 120 versus 130. So we might report it as a whole number, but it's a pressure. You could have a pressure of 120.1 or 120.05 or whatever. We just choose to round it that way. And of course, we choose to develop instrumentation that's only accurate to that level. There's no sense in spending a whole bunch of extra money getting an instrument that has 4 decimal places of accuracy when we're never going to use any of those decimal places of accuracy. Something like grade, well, this would be discrete, right? If I'm at C, the next allowable grade is B or D, depending on which way you're counting, I suppose. So I would say this would be kind of more discrete. But grade kind of breaks the mold a little bit because they're letters and not numbers, so it's a little bit of a strange one. It kind of has the feel of a quantitative because it has a natural ordering, but it's also not numerical. So some of these ideas like rounding and so on kind of don't apply so nicely to grade. And kind of generally speaking, if we have a variable that starts with number of students, number of cars in a parking lot, number of plane trips in a year or whatever, those things tend to be discrete. So if I see the prefix number of, that's probably signaling a discrete variable. But those aren't necessarily the only discrete variables. So if we think about something like age and salary, they can be a little bit tricky. And again, I think it's useful to kind of zoom out a little bit for a second and think back, why are we doing this? Why are we coming up with these definitions and sorting variables into these different categories? Well, again, it really has to do with coming up in maybe chapters 2 and 3 or in later chapters. We might have different analytical techniques that we want to use for, say, discrete data versus continuous data. We might have different choices of how we want to set up a graph or something like that, whether we have a discrete versus continuous variable we're talking about. So it's about the information that I want to communicate and in what way. So that being said, there are going to be some gray areas, right? When we try to take something that's very nicely philosophically divided like this, discrete versus continuous or qualitative versus quantitative, and I try to overlay that structure onto the real world, which doesn't care at all about my philosophy, there are going to be some things in the real world that kind of, straddle the two, that are kind of gray areas, in part because we're not, infinitely precise in our description of what we're talking about, but also in part because we're trying to overlay a model onto the real world, again, that is wrong, but maybe useful. So let's think about, say, age. Would you say that age is discrete or continuous? And what would be your reasoning?
I would say continuous because are you counting it in years or in months or in days? Or in
Yeah,
hours?
exactly. You could say, you know, I'm 30 years old, or I'm, you know, whatever number of days you are old, or whatever number of minutes you are old, or seconds or milliseconds. You could get more and more precise about what you mean. So we could say age in fractional seconds would be maybe something that's continuous. Can anybody make an argument for why why some representation of age might be discrete?
I would suppose if you're looking at an age range, like so sometimes you're asked if you're in the 45 to 55 range, or if you're in the 55 to 65 range, then that's absolutely discrete. So
Yeah, yeah. Or kind of, put roughly another way is if we were thinking of age as number of complete life years, right? So if you say how old are you and somebody says 30, really what they mean by that is they've completed 30 full life years and have not completed their 31st full life year. Well, there's that number of again, that kind of signals a discrete variable. So again, when we say, well, I want to measure somebody's age, if I was really developing or designing an experiment and coming up with the tools and techniques I want to use to present that information, I might have to think a little more carefully about this. Do I mean like fractional seconds, or do I mean like number of complete life years? That might lead me to two different choices for ways I want to represent the data, and one or the other might be the more important way for me to think about age for whatever it is that I'm talking about. If we were to think about something like salary, again, discrete or continuous, any thoughts on that? Say like annual salary.
What if they have like bonuses like in between the salary? Would that like, I don't know where that would fall into it.
Yeah, we would just kind of lump that in with, if you got your bonus this calendar year, then that counts toward your salary. So if we wanted to be more precise, we could say something like, oh, gross income or whatever number that is on your W-2, like the wages, tips, and whatever number.
Then would it be considered discrete?
So we could argue that it's discrete. And what would be the argument that it's discrete?
Based on like the lump sum you get. So then like that's the only thing being like valued towards the
So again, though, we have to be really careful that discrete versus continuous is not a temporal question. It's not a question of whether we continue to get more information or not. It's a question of how we actually measure what we have. So if I was going to report an annual salary to you, is it more like something that has to be rounded, or is it more like something that I can get more precision if I do a little more work? So the argument for discrete would be, well, your salary can't be an increment smaller than a cent, right? So somebody can make $50,000 or 50,001 cent or 50,002 cents. I can, for any given potential salary, I can say what the next one is. I just add 1 cent to it. So the next idea is well defined. Or between any two salaries, like $50,000 even or $50,000 and 1 cent, there's no other possible salary. You can't make $50,000 and a half a cent in a year. Our banking systems and so on don't allow for that, even if you're not being paid in cash. So I guess if you've ever seen Office Space, is it Office Space or I think so, right? The one where they like have some kind of crazy thing where they pull off all the fractional cents, but that's more fiction than reality, I think. So we could
okay,
argue
yeah.
it's yeah.
I definitely see your point. So then
Yeah.
we'd have to round it. So it'd definitely be the other one.
Yeah, so on one hand, we could argue it's discrete because we go by sense, right? On another hand, we can say that, well, if I was going to represent this data, do you really think I'm going to like make a list of all of the potential salaries from 0 to 1 cent to 2 cent, all the way down, to whatever 50,000 point, 7 cents and all the way am I going to make a list of all of these and then count, say, the number of people who have exactly that salary? Well, no, because then I just have a list of like a ton of zeros and an occasional one, a bunch more zeros and a one, and that's not going to be practically useful. This is more like something like height or weight, mainly because with salary, I don't think anybody really cares if you get plus or minus 1 penny, or even plus or minus $1 in a given year, right? We care about maybe things on the scale of 10 or $100, tens or hundreds of dollars. So effectively, we have more decimal places of accuracy than we're likely to ever care about. So in a sense, we could argue that this is continuous. Again, this is one that kind of straddles the two, right? What am I interested in when it pertains to salary? If I'm looking at the average income of people in Pittsburgh, I don't really care whether it's this versus this versus this. That's of no consequence to almost anything. So I'm effectively rounding. I effectively have more information than I ever want anyway. So I could model it as continuous. But if I wanted to be really pedantic, I could argue it's discrete because we can only go in increments of 1 set. So there are things that are gray area, like I would argue, something like salary or age are kind of gray areas. But I think the rest of these fall pretty clearly, maybe even blood pressure. But I think the rest of these fall pretty clearly into one or the other. Okay, and let's kind of just introduce the idea of measurement scales. We'll come back to this next time. But measurement scales looks at this same kind of idea, but in a slightly different way. So measurement scales also has to do with how much underlying structure is there in the data that we collect. And this directly affects what, particularly in chapter 3, what quantitative descriptive statistics we can report. So can I compute an average? Well, if I want to compute an average, I need to add a bunch of things together. Well, are these things that are sensible to add together? I can't add together, Democrat plus Republican plus Libertarian plus Democrat plus Independent plus Republican. That doesn't make any sense to do. The addition operation doesn't make sense on political parties, but it does make sense on maybe, say, height in inches. So that's really what we're looking at here. We have 4 different measurement scales, and each one has a little bit more underlying structure to it, and there are more operations that can be done on each successive, more mathematical operations that can be done on each successive measurement scale. The bottommost measurement scale is nominal data. All that we're doing here is we're classifying data into mutually exclusive categories. They have no natural ordering or ranking, so we can't even put them in an order, let alone do arithmetic operations like addition or division or something on them. We can't even order them. Well, nominal measurement scale essentially corresponds to qualitative data, this kind of categorical data. We just have categories of different political parties that you can slot the data into. Or we have categories of, different cities. Do you live in this city or that city? We can slot the data into those different categories, but no ordering or ranking. Ordinal has a little bit more structure to it. There are categories, but they can also be ranked. So there is a natural ordering and ranking. Now, when it says can be ranked, we mean naturally. We mean in a way that is fundamentally linked to the thing we're studying. I mean, you can rank anything. You can just choose an order for it or put it in alphabetical order, but that doesn't have much, it doesn't typically have much relationship to the thing we're actually studying, just some arbitrary order that we choose to impose on it. So for ordinal, there's a natural ordering or ranking. There's something that's inherently tied to the thing we're studying. That, you know, this outcome has more of that thing than this other outcome. Right? If you're if you're in this city versus that city, you're not like inherently in a more something geographic location than the other city. They're just two geographic locations. But ordinal would have a meaningful ranking. However, differences in the sense of subtraction is not meaningful. So nominal we can't order. Ordinal we can order, but we can't really do arithmetic operations on it. And then we have interval and ratio. So interval, we do have ordering, we can rank. And we also have meaningful differences. So subtraction makes sense. Differences between two values are sensible. They mean something inherently about the thing we're studying, but there's no meaningful zero. So if I see a measurement of 0, that doesn't inherently tie to the idea of there being none of that thing. And then ratio, so interval, we can do subtraction, but we can't really do division. So ratio, we can do division as well. We have a meaningful 0, ratio data, ratios make sense. So if I say that one measurement is twice the other, that means that that thing has twice as much stuff that we're interested in than the first thing. So again, we come back, I might supplement a couple of these with a couple other examples, and then we'll look at each of these and try to decide which measurement scale they would typically be on, and then we'll continue on with the chapter 1 PowerPoint from there. Are there any questions on anything? Let me stop the recording.